Hello there and welcome to the big long video that's going to go through a lot of questions to do with proof by contradiction. This is a topic that students typically hate every year. I always get loads of complaints that I can't do proof by contradiction, generally because it's done right at the start of the year and then it's tested at the end of the year. So you need a kind of recap as to how to do it when you get towards the end of the year. And also it's a pretty tricky topic in and of itself. So I just want to go over the idea of proof by contradiction before we get started. It's always good to see the basic outline of a typical question. So a typical question will start by saying theorem is that statement A, whatever statement A is true. And the way you're going to answer it is by saying that statement A is false, saying the complete reverse of statement A is the actual true thing. And then what you'll do is you'll work through some mathematics and you'll do da 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 da, and then you'll get to a point where you've got statement X, a completely different statement, not might be related to statement A, but not exactly statement A. Statement X is true and statement X is false. So given this assumption here that statement A is false, we've been led mathematically to something that is just completely factually untrue. You can't have a statement that's true and a statement that's false happening at one time. That's the contradiction. So if we get a contradiction saying that something is true and something is false, then we must conclude that our initial assumption that statement A is false must be false itself. And when you've got a double falsehood, you've got statement A is true. So that's the basic outline of a proof by contradiction. Now, the difficult part is you're not always sure what this statement X is before you get started in the question. And this is kind of what's quite intriguing about proof by contradiction to me, is that when you start a question, you're not too sure what alley you're going to go down. But the more practice you get, the more familiar you get with types of questions, and the better you'll become at doing this. And generally, a good bit of a hint as well is that statement X relates to statement A being false. There must be some property of statement A being false, and that will define statement X, and then you'll be led down an algebraic path that will say that yes, this is true, but also this thing here is false, and that's the contradiction. So just to go through a brief outline, so you've got something on the side of your page while you work through it. If the question is A is true, then you say A is false. You do some algebra, and then you get to a point of contradiction where X is true and X is false. So therefore it must be the case that A is true. So let's leave that on the side while we work through the first question, which is the square root of 2 is irrational. So this is what I've got to prove correct here, and I'll do it by creating a contradiction. So the first thing I need to do in my answer is reverse this statement. It's to do the reverse of statement A, and the reverse of something being irrational is that that something is rational. So I'm going to assume that the square root of 2 is rational. And then generally statement X is created by some property of A being false. So it's created by something to do with this. Now when root 2 is rational, it can be represented as a fraction. So I'm going to say that the square root of 2 is represented as A over B in its simplest form. In its simplest form. Now this statement here is actually going to be statement X when I get to my contradiction. I'm going to prove that A over B is not in its simplest form. And the reason that I can do that, the reason I'm going to assume this, is because all fractions can be reduced into their simplest form. So I've just taken the fraction of root 2 and simplified it into its most simplest form. And even when it's in its simplest form, it can be simplified again, which is a contradiction. So that's eventually where I'm going to lead to, but I'm going to start off with some algebra. So therefore, the square root of 2 is equal to A over B. And I'm just going to do a bit of rearranging now, so I'm going to times both sides by B. So the square root of 2 multiplied by B equals A, and then I'm going to square both sides. So it's going to be 2b squared equals a squared. Now from this little statement here, if I've got 2b squared on the left-hand side, then a squared here, this left-hand side must be even. And if the left-hand side is even, then so must the right-hand side. And if a squared is even, then a is even. The only way you can square a number and it comes out as an even number is if the starting number before you squared it was an even number to start with. Think about it, 6 squared is 36, that gives you a even number. But if you take an odd number like 9 squared is 81, which is an even number. So there's a perfect mapping between odds to odds and evens to evens when you square. So if a is an even number, then I can write a as 2c. Because any even number can be represented as 2 times something else. So I'm now going to use a equals 2c in the next part of the proof. So I'm now going to replace this with 2c, and then expand the brackets on the right hand side. So I'll get 4c squared, and then I'll divide by 2 on both sides, and I'll get b squared equals 2c squared. Now from this statement here, the right hand side is clearly even, and so must therefore the left hand side be. Now if b squared is even, the only way I can square a number to get an even answer is if b was even to start with. Now this will contradict the fact that a over b is in its simplest form, because if I've got a fraction where it's an even number on top of an even number, then I can reduce it by a factor of 2, and I'll have to explain that in the next sentence. As a and b are both even, the fraction a over b can be simplified. So what I've got here now is a statement that says that a over b is in its simplest form, and I've got a statement here that says a over b can be simplified, which is the contradiction. So statement X is referring to the simplification of the fraction a over b. A over b is simplified and a over b is not simplified. A over b can be simplified, and this is so this assumption that the square root of 2 is rational has led me to this contradiction, which can't be true. It's absurd to be true. So therefore the only thing that I can say is that my assumption must have been false, so therefore the original theorem must be true. Therefore root 2 must be irrational. Because if something like the square root of 2 being rational has led me to this contradiction, then that assumption cannot be true. So it must be the case that root 2 is irrational. Okay, so square root of 2 is a pretty famous proof by contradiction theorem, and so is this one here. There are infinitely many primes. So when I'm doing I'm trying to prove that there are infinitely many primes, the way I do proof by contradiction is I start by saying that this is false. So I'm going to assume there are, what's the opposite of infinitely many primes? Finitely many primes. So assume there are finitely many primes. And what can I do to create a statement X that I will eventually have a contradiction in? Well, if there are finitely many primes, then I could create a complete list of all of those prime numbers. So therefore, the list P1, P2, P3, and all the way up to the highest prime number, Pn, is a complete list of prime numbers. Is a complete list of primes. Okay, so now what I'm going to do is I'm going to try to create a contradiction here. So what I'm going to do is I'm going to try and create a new prime number, one that's not already in this list. So I'm now going to create the number n, and I'm going to multiply all of these prime numbers together. But that won't give me a prime number. But what I could do now is I could add 1 onto this multiplication of all the prime numbers. Now what will happen here is when you divide n into its prime factors, what's going to happen? Well, you'll always get a remainder of 1 if you try and divide by any of these prime numbers that we've already found. If you divide n into its prime factors, you will always get a remainder of 1 when dividing by any number in the list. So it looks like n is going to be prime. So therefore, n is either prime itself or n could divide by a different prime number that's not in this list, or n can divide by a prime number not in the list. And either of these two options, either n is prime itself or there's another number n not in the list, that will contradict the idea that the list is a complete list of primes. So what we can therefore say is, therefore, the list is not complete. The list is not complete. And there's your contradiction. We've got statement X, which is the list of primes is complete, and we've just shown that statement X is also false, that it is not complete. So our assumption to start with that's created this contradiction must therefore be false, and therefore we're getting a double falsehood, which means that statement A, the statements that we started with, must therefore be true. So therefore, there are not finitely many primes there are infinitely many primes. And there we are, that's the answer to this question here. Let's now move on to the next one. Okay, so the next one is the square root of 3 is irrational. Now the outline for this proof is going to be very similar for the square root of 2 is irrational, so definitely pause the video, have a look at how you proved square root of 2 is irrational, and therefore you can probably use the same kind of ideas proving that square root of 3 is irrational. So we're going to start by assuming the opposite. Assume root 3 is rational. And if root 3 is irrational, it can be represented as a fraction, a over b, in its simplest form. It's not too much of an assumption to assume that it's a over b is in its simplest form, because fractions can always be simplified into its simplest form. So let's now start with some algebra, and then times the b onto the other side, and now square both sides. So now from this little algebraic statement here, the left hand side is a multiple of 3, and so is the right hand side, because if the left hand side is equal to the right hand side, then the right hand side must also be a multiple of 3. So a squared is a multiple of 3. And if a squared is a multiple of 3, then a must be a multiple of 3. So if a is a multiple of 3, then it can be represented as a equals 3 times c. And now I'll bring this into my algebra. 3b squared equals 3c squared, because I know that a is a multiple of 3. Expand the brackets on the right hand side, divide by 3, and now I know that the right hand side is divisible by 3, so therefore b squared is a multiple of 3. And if b squared is a multiple of 3, then b is a multiple of 3. And if b is a multiple of 3 and a is a multiple of 3, then a over b is not in its simplest form. Therefore, a over b is not in simplified form. So there we are. When I refer to statement x is true and is not true, you can clearly see it here. A over b is in its simplest form, a over b is not in its simplest form. So how two things can simultaneously be correct and incorrect is just absurd. Like, you can't have two things that are correct and incorrect. So therefore the assumption that got us to this absurdity is an incorrect assumption. So therefore root 3 is not rational, because if I assume that it is rational, then I've got myself to an absurdity. So root 3 is not rational, root 3 is irrational. And there we are, that's the answer to that question. Okay, so moving on to the next question then. Log 2 base 3 is irrational. This is what we've got to prove. It's another irrational question, so it might be similar to root 2 and root 3 being irrational, but there might be a different way that we have to go about proving it. But we do start with the assumption of the opposite. Assume that log 2 of 3 is rational. And once you've assumed that something is rational, then you can assume that it's equal to a over b. Okay, so let's assume it's equal to a over b, and and then we'll start rearranging this algebraically. So I can rearrange this by saying that 3 equals 2 to the power of a over b. And the next thing I'll do is I will raise everything to the power of b. So it's going to be 3 to the power of b equals, I'll make sure I spell it out clearly here, 2 to the power of a over b to the power of b. Now when you've got two powers multiplying together here, so one power of another power, you multiply your power numbers. So it's going to be 3b equals 2 to the power of a, because we've got a b times a over b. So it's just a. Now so a and b here are integers. Let's just write that down at the start. A and b are integers. And if a and b are integers, then it's going to be 3 times 3 times 3 times 3, b times equals 2 times 2 times 2 times 2 times 2 times 2. And that's clearly going to give an odd number on this side equals an even number on this side, which isn't going to really make sense unless we do it to the power of 0. So actually, this could work if we use a equals 0 and b equals 0. That's the only solution to this question, is the only solution. Otherwise, left-hand side is odd and right-hand side is even. That's the only way it's going to be true. But it wouldn't really make sense, if we look back at our assumption here, a over b, it wouldn't really make sense that b is 0, because you can't have a 0 on the bottom of a fraction ever. So what I'll also say back up here, so I'm actually going back up to where I was writing in the question, is that b is not allowed to be 0. That is a fair enough assumption to say for a fraction that the denominator is not allowed to be 0. So here is where statement x comes in. Statement x is that b is not 0 and b is 0. How can that be true? How can b simultaneously be 0 and simultaneously be not 0? So this part here is statement x is true and statement x is false. B is 0, that's the true statement, and b is not 0, that's where x is false. So this is kind of like the x statement for this proof here. So this is a contradiction. This is a contradiction. It's always good, I don't know if I've done it yet, but I can't remember, to always get the word contradiction into your conclusion. This is a contradiction that b is 0 and b is not 0. So therefore what we assume to start with to end up at this contradiction must be false. So therefore log 2 of 3 is irrational. Because if it were rational, it would lead to something absurd. Okay, let's move on to the next question. And the next question is, there does not exist integers a and b such that 15a plus 20b equals 3. Well, let's start, as all proof by contradiction theorems, so all proof by contradictions do, which is to assume the opposite. So assume that there does exist. Assume that there does exist a and b that are integers such that 15a plus 20b equals 3. Okay, so what we might want to do with this bit of algebra is divide by 5. 3a plus 5, so plus 4b equals 3 divided by 5. And now what we've got here is something that really kind of doesn't make sense, because if a is rational, so if a is, it's not rational, that's not the word, an integer, then 3a is an integer. That's pretty easy that that is an integer. An integer is just a whole number. If b is an integer, like we're assuming it is, then 4b is an integer. And it's clearly the case that when you add two integers together, you get an integer. But 3/5 is not an integer. It's not a whole number. So therefore 3a plus 4b is not an integer. Because we've got up here that 3a plus 4b is 3/5, so therefore 3a plus 4b is not an integer. And here is where we have the contradiction. We have the contradiction here, where we are told, where we've worked out from the fact that a and b are integers, that 3a plus 4b is an integer as well, and that 3a plus 4b is not an integer, and that's clearly not true. You can't have simultaneously these two things existing in the universe. So yeah, there must be a contradiction here. So what we assumed to get this contradiction must therefore be incorrect. So therefore, there does not exist a and b, integers a and b, such that uh, 15a plus 20b equals 3. This is a contradiction. It's always good to write the word contradiction when you're doing a proof by contradiction question. There we are, that's the answer to that question. Okay, so let's have a go at the next question then. The next question is prove that there is no greatest integer. So let's start where all good proof by contradictions start, which is to assume the opposite. Assume there is a greatest integer. And we can give it a value. We can give it the letter n. So the thing with integers is you can always add one to get a new, bigger integer. So let's now consider n plus 1. This is an integer. So whenever you add 1 to an integer, you get the next integer up. And also, n plus 1 is bigger than n. So therefore, n is smaller. N is smaller than n plus 1. So n is not the greatest, which is the contradiction. N is the greatest, and n is not the greatest. So therefore, there is a contradiction. Always good to write the word contradiction. And there is no greatest integer. And there we are, that's the answer to that question. Okay then, moving on to the next one. Log base 5 of 7 is irrational. So again, with the irrational type proofs, we assume the opposite, and the opposite of irrational is rational. So assume log base 5 of 7 is rational. So, therefore, if it is rational, then we can express it as a fraction, is equal to a over b. Now, last time I remember in this proof, it was really important that b was not allowed to be 0, so I'll include it in my definition of my fraction here. And let's now rearrange this, so 7 is going to equal 5 to the power of a over b, and now we'll do b to the power of both sides, so 7 to the power of b equals 5 to the power of a. Now, because last time I used the facts of odds and evens, the 3 to the power of b is equal to 2 to the power of a, we had an odd expression on the left and an even expression on the right, but here we're both going to have odd and odds. So we're going to have to have a different explanation here, and the explanation is going to be because 5 and 7 are co-prime, 5 to the power of a is just going to be 5 times 5 times 5 times 5 times 5, so that will just have a prime factor of 5 in it, and 7 times 7 times 7, however many times you multiply 7 together, will only have a prime factor of 7 in it. So co-prime means that they don't share any prime factors. So because 5 to the power of a and 7 to the power of b are co-prime, the only solution is a equals 0 and b equals 0. And we set up before statement x, which was that b could not equal 0, and we've got a falsehood to that, so we've got the reverse of that happening down here. We've got b equals 0. So therefore, there is a contradiction that b does not equal 0 and b does equal 0. So where we started to get to ourselves to this contradiction must be incorrect. So therefore, log base 5 of 7, which started this whole thing off, must be irrational. And there we are, that's the answer to the question. Okay, so let's move on to the next one. So there does not exist integers a and b such that 6a plus 9b equals 1. And the really important part of this statement here is that a and b are integers. If a and b were fractions, then yeah, you could have some fractions where 6a plus 9b would equal 1, but we can clearly see that the left-hand side here is a multiple of 3, and the right-hand side is not. So how can you have one thing that's a multiple of 3 equaling something that's not a multiple of 3? So that's where we're going to be heading with this question. But we need to set up the structure for the proof first, and that will be assume the opposite of this statement. Assume there exists. Because if we want to prove there does not exist, we'll assume the opposite, which is that there does exist. Assume there exists integers a and b, integers, such that 6a plus 9b equals 1. And just to make it really obvious that there's a factor of 3 here, we can start off the algebra by dividing by 3. So let's do 2a plus 3b equals 1/3. Okay, so what we're now going to do is we're now going to claim that the left-hand side must be an integer, because it's made up of integers and additions, and then the right-hand side is clearly not an integer, because it's a fraction. So we'll have to now start to state our case. So the left-hand side, 2a is an integer, 3b is an integer, and 2a plus 3b is also an integer. So the left-hand side here is an integer. And on the right-hand side, it equals a third, which is not an integer. And there's our contradiction, that we have 2a plus 3b, which is an integer from our logical steps on the left-hand side, and we have 2a plus 3b on the right-hand side, which equals a third, which is not an integer. So there's statement X for you. Its statement X is that 2a plus 3b is an integer, and 2a plus 3b is not an integer, so it's true and false at exactly the same time. That's completely absurd, so there's the contradiction. Therefore, there is a contradiction. Always good to put the word contradiction in a proof by contradiction proof. There is a contradiction. Therefore, what we assumed to start with that led us to this contradiction must be false. So we've got the double negative happening here, which means that the original statements must be true. So therefore, there does not exist A and B. And there we are, that's the answer to this proof. Let's move on to the next one. Okay, so let's move on to the next one then. Prove that triangle ABC has no more than one right angle. Okay, an interesting one here. So let's assume the opposite, because that's where you always start in a proof by contradiction. Assume that in triangle ABC, there are two right angles. Okay, so we need to create a statement X that will lead us to a contradiction. So we'll say that let's make it very clear. All three angles in a triangle must be greater than 0. And that statement X that we're later on going to have a contradiction in. Because if two angles were right angles, and there is 180 degrees in a triangle, so if there are two right angles and there are 180 degrees in a triangle, the third angle must be 0. Which is where the contradiction comes in, because the contradiction is that all angles must be greater than 0, and the third angle must be 0 is a contradiction. Therefore, there is a contradiction. So the thing that we assumed that led to this contradiction must be false. Therefore, we get the double negative at A is false, which means that A is true. Our original statements that we're looking to prove is true. So therefore, triangles have no more than one right angle. And it's quite interesting here, looking back at this question that we've just answered, a maths question only has kind of 1, 2, 3, 4 numbers in it, and that's within the context of sentences. So what we've done here is mathematically we've laid out a detailed logical proof, which is what maths kind of is. We use generally numbers to do that, but in this case we've just used logical arguments from mathematical properties to get a contradiction, in which case the original statement must therefore have been true. Lovely, let's move on to the next one. Okay, so let's move on to the next question. The question is, prove that there is an infinite number of even numbers. So even numbers are integers, and we'll start by assuming the opposite of this statement. So we'll assume that there is a highest. Assume there is a highest even number. Okay, so we'll call it 2n. And now to prove that this is factually incorrect, we'll consider the number 2n plus 2. We can factorize this to 2n plus 1. This is an even number, and also 2n plus 2 is greater than 2n. So therefore, 2n plus 2 is larger than 2n. And to really prove the contradiction here, 2n is not the highest even number. Because you can always just add 2 to get to the next even number. It's not the highest even number. Okay, so there we are. So therefore we have a contradiction. We have 2n is not the highest number and 2n is the highest number, which is a contradiction. So therefore there is a contradiction. And so therefore the assumption that we use to get to this contradiction must be false, double negative, so therefore the original statement must be the correct statement. So therefore there is not, there is an infinite amount of even numbers. So there we are, that's the answer to this question. Let's move on to the next one. Okay, so this is the next one. Prove that there does not exist integers a and b such that 20a plus 30b equals 7. And we've done a few of these before, so hopefully you're now starting to spot patterns between the questions that they can ask in proof by contradiction questions. We start with the opposite of this statement, so assume the converse, so assume there does exist integers a and b such that 20a plus 30b equals 7. Okay, so then we go for the approach of dividing by a common factor between 20 and 30, then going for integers on the left, non-integers on the right. So consider 20a plus 30b equals 7, and we can clearly see here there's a factor of 10, so if we divide by 10, then we get this expression here. And in this expression, on the left-hand side, 2a is an integer, whole number. 3b is an integer. So therefore, 2a plus 3b is an integer. And on the right-hand side, we have 7 over 10, which is not an integer. So the contradiction here is that 2a plus 3b equals an integer, and the thing that equals 7 over 10, which is 2a plus 3b, is not an integer, which is a contradiction. So the statements that led us to this contradiction must be false. A is false, that was this thing here, that must be false, so it's a double falsehood, so therefore the original statements must be true. So therefore, there does not exist A and B. And there we are, that's the answer to that question. So let's move on to the next one. And we're going to move on to some slightly different types of proofs by contradiction where we've got a conditionality statement. So something like this. If statement A is true, then it follows on that statement B is true. So the way that we reverse the initial part of the proof is we keep the first part of the statement the same. So statement A will remain true, and then it's anything after the then word. A key word in this sentence in the theorem is then, because anything after then is negated. So if statement A is true, keep that statement A to be true, then statement B is false, or statement B is false, and there we're going to get our contradiction. So we'll do some algebra, we'll set up some rules to do with statement A being true and B being false, and then we'll prove that some statement connected to this statement above, but maybe not the same. Statement X is true and statement X is simultaneously false. So therefore, the statements that led us to this contradiction must be incorrect. So therefore, this statement here is incorrect. So the opposite of this statement must be correct, which is this statement up here. So therefore, we must conclude that if A is true, then B is also true. And the difficult part is that you are not always sure what statement X is. Sometimes statement X is actually the same as statement A. It can't be statement B because that's not how proof by contradictions work, but it sometimes is statement A. You might end up finding that statement A is true because it says it's true up here, and statement X is false, and that might be your statement A, or it might be a different statement, but I'll show you a few examples now. So this is the proof that we'll go through in a second. So if A is true, then B is true. What you do to start with is keep A true, but turn B to be false. Do your algebra, and then find a statement X that is simultaneously true and false. And that can be statement A as well. So therefore, if A is true, then B is also true. Okay, so let's have a go at this question up here then. So if A squared is even, then A is even as well. So we've got a keyword of then in it, so anything before the word then will keep the same. So we're going to assume A squared is even, and then anything after the word then we're going to reverse. So and A is odd. Okay, and we're going to carry on with this statement here that A is odd. So if A is odd, it can be represented as 2n plus 1. It's an odd number. And now let's have a look at what happens to A squared. You've seen this kind of proof before. 2n plus 1 squared, that will be 4n squared plus 4n plus 1. And let's just really emphasize that this is an odd number by writing that it's 2 times something plus 1. It doesn't really matter what that something is inside the bracket here, but it's double something and then add 1, which will make this an odd expression. So therefore, what we've got here is that simultaneously A squared has to be even and A squared has to be odd. So statement X here that is providing the contradiction is statement A. It is the first part of this statement here that is being contradicted here. We have A squared is even and A squared is odd. So the statement is true and it is also false. So therefore, the assumption that led us to this contradiction must be incorrect. So therefore, if that is incorrect, then the opposite of that must be correct. So therefore, this initial statement is correct. So therefore, if a squared is even, a is even as well. And there we are, that's the answer to this proof by contradiction. Okay, so let's move on to the next question. So again, we've got the word keyword then in this statement here. So in our assumption, we're going to keep everything before then true. So assume A is rational, B is irrational, and A plus B. Now after the then, that's when we change the statement round to a false. So then A plus B is rational. So we're going to assume this and then get ourselves to a contradiction. So let's pick up this bit here and have a look at what that will mean. So if A plus B is rational, then it must be represented as a fraction. Let's write it as x over y. But also we know that A is rational, so we could also write A as a rational term as well. So this is rational, so that can be represented as a fraction. A plus B is rational, so therefore that can be represented as a fraction. So let's call A u over v. Now B here is not being represented as a fraction because it's irrational, so it can't be represented as a fraction. But if I now do the algebraic manipulation of take away u over v from both sides, then B is equal to x over y minus u over v, and I could simplify this fraction here. It would be xv minus uy over vy, which is a fraction, which is a rational value. So therefore B is rational, which contradicts the fact that B is irrational, which is a contradiction. So therefore, these statements that we've used to get to this contradiction must be false. So therefore, the original statements must be true. So therefore, if A is rational, B is irrational, then A plus B is irrational. So there we are, that's the answer to this question. Okay, so moving on to the next one. If A squared is a multiple of 3, then A is a multiple of 3. So keyword then is in this sentence as well. So when we do our assumption, we'll assume that A squared is a multiple of 3, and A is not a multiple of 3. And this is slightly more difficult because it's not just a case of odds and evens, it's a case of not being a multiple of 3. So actually there are two situations that could occur here. Case 1 is that A is represented as a number 3n where it has a remainder of 1 when it is divided by 3. And case 2 is that A is a multiple of 3 but will have a remainder of 2. So when it's divided by 3, we'll have a remainder of 2. These are the only two situations that could occur. Every number is either, if it's not a multiple of 3, it's either 1 more than a multiple of 3 or 2 more than a multiple of 3. And that satisfies every single number that A could potentially be if it's not a multiple of 3. So let's now have a look at what we'd get when we square this on both situations. So that's going to be 9n squared plus 6n plus 1. And then this one here is going to be 9n squared plus 12n plus 4. Now, either way, this number over here is going to be 3 lots of 3n squared plus 2n plus 1. So it's not going to be a multiple of 3. And this one over this side is going to be 3 brackets 3. So 3n squared plus 4n plus 1 plus 1. So that's also going to be, when it's divided by 3, we'll have a remainder of 1. It's 1 more than a multiple of 3, and this is also 1 more than a multiple of 3. In either case, a squared is not a multiple of 3. Which is a contradiction. So there we are. So the statements that led us to a contradiction must be false. So therefore, if a squared is a multiple of 3, then so is A. And there we are, that's the answer to this question. Okay, so let's move on to the next one. And the next question says, if a squared is odd, then A is odd. So we've got the keyword of then in this sentence, so we're going to negate everything after then. So we're going to assume the first part is true, A squared is odd, and then everything after the n is going to be the opposite. So A is even. So that's what we'll assume then, and let's start off with A is even. So if A is even, it could be represented as 2 times n. So A squared will therefore be 4n squared, which is another even number. Clearly it's an even number because it's 2 times something. A squared is even, so therefore that there is a contradiction. There is a contradiction. There's a contradiction here where a squared is even, and here where a squared is odd. So the statement X is that a squared is odd, and that's also false because a squared is even. So therefore there is a contradiction, so therefore the statements that led us to that contradiction must be incorrect. So therefore if a squared is odd, then a is odd as well. So there we are, that's the answer to this question. Okay, so let's move on to the next one. So let's go for the assumption. The statement here is that if A is irrational, then A plus 2 is also irrational. So let's set up our assumption. So assume A is irrational. And then the keyword is then, and then anything after the then word is the opposite. So and A plus 2 is rational. So if A plus 2 is rational, then it can be represented as a fraction. A plus 2 equals, let's refer to it as x over y. And now let's take away 2 from both sides. So it would be A equals x over y minus 2. But I could simplify that into one fraction. I could represent it as x minus 2y over y, which is rational. So therefore, we have a contradiction. We have A is rational and A is irrational, which is a contradiction. So therefore, if A is irrational, then A plus 2 is irrational. And there we are, that's the answer to this question. Okay, so moving on to the next question. If A plus B is irrational, then at least one of A or B is irrational. So let's do the assumption first, as always. So the first part will keep the same. A plus B is irrational. And then we get to the word then, and then we have to swap over everything or negate everything on the either side of that then. So at least one of A or B is irrational, so that means that either A is irrational, B is irrational, both of them are irrational. So the only thing that's opposite to that is that A or B are both rational, and A and B are rational. Because that is the opposite statement to at least one of A or B is irrational. So if A and B are rational, then A we can write as U over V, and B we can write as X over Y. Then A plus B will equal U over V plus X over Y, and we can simplify that together, UY plus Vx over Vy, which is rational. Which is a contradiction, because I've now just shown that A plus B is rational and A plus B is irrational in our assumption, so which is a contradiction. So therefore, the statements that has led us to that contradiction must be incorrect, so therefore the original statements must be correct. Therefore, if A plus B is irrational, I'm going to finish this off just by writing ... because I'd write then at least one of A or B is irrational. And there we are, that's the answer to this question. Okay, so let's move on to the next one. So if n cubed is odd, then n is odd. So once again, we'll do the assumption. So assume the first part remains true, so n cubed is odd. And then when you get to the word then, you negate everything past then. So and n is even. Okay, so if n is even, then n can be represented as 2x. So then n cubed can be represented as 2x cubed, and that will be 8x cubed. But we could do a little bit of factorising just to really emphasise the fact here that this is an even number. It's 2 times something, which makes it even. And then we have our contradiction. N cubed is odd, and n cubed is even, which is a contradiction. So therefore, if n cubed is odd, then n is odd as well. So there we are, that's the answer to this question. Okay, so moving on to the next one. The next one says if A is rational and AB is irrational, then B is irrational. So let's start with that assumption again. So assume A is rational, AB is irrational, and now that as soon as we get to the word then, we negate everything past then, and B is rational. Okay, so let's get involved with these rational terms here. So if A is rational, then A can be represented as U over V. And if B is rational, then B can be represented as X over Y. So therefore, when you do A times B, which is going to be U over V times X over Y, you get UX over VY, which is rational. And there's your contradiction, because A times B is irrational, and also at the same time AB is irrational, which is a contradiction. So statement X here is the statement that AB is rational, but because it's also irrational, which is a contradiction. Okay, so therefore, if A is rational, AB is irrational, then B is irrational. And there we are, that's the answer to this question. And moving on to the final one of these types of questions, if A is irrational and B is rational, then B is irrational. So let's go for the assumption then. So we keep the first part the same. Assume A is irrational. AB is rational. And as soon as we get to the then word, we negate everything past here, and B is rational. Okay, so if B is rational, let's start with that one. B is rational. So therefore, B can be represented as X over Y. And also AB is rational. So therefore, AB can be represented as a different fraction, U over V maybe. So therefore, we have A times by X over Y, which is B, equals U over V, which is AB. I've set up a statement here, which is A times B equals AB, which is pretty obvious. Now let's times by Y and divide by X, and therefore we get UY over VX is equal to A, which is rational. Which is a contradiction, because A can't be rational and irrational at the same time, so the statement that was made that got us to this absurdity must be incorrect, so therefore the original statement is correct, which is a contradiction. So therefore, if A is irrational, AB is rational, AB is rational, then B is irrational. And there we are, that's the answer to this question. Okay, so let's move on to these 4 extension questions now. So question 1 for the extension is, if A, B and C are integers such that A squared plus B squared equals C squared, then one or both of A and B must be even. So let's set up that assumption step first on the proof by contradiction. So assume A squared plus B squared equals C squared, and because anything after the then has to be negated. So one or both of A and B must be even, so that means either A is even, B is even, or they're both even. The only thing that's not that, or the opposite of that, is A and B are both odd. Okay, so let's get started then. A is odd, so it can be represented as something like 2x plus 1. And B is odd as well, so that can be represented as something like 2y plus 1. And then when we take these two expressions and we do a squared plus b squared, we're going to get 2x squared, so 2x plus 1 squared plus 2y plus 1 squared. And then that's going to equal, so let's expand the brackets on both of these, 4x squared plus 4x plus 1. And on the second one, it's going to be 4y squared plus 4y plus 1. And for a reason I'm just about to explain, I'm going to factorize out the 4 here. And then I'll have to add 2 on the end. So what we're saying about the a squared plus b squared is that it's going to be 2 more than a multiple of 4, which will equal c squared. But a little fact about square numbers is that square numbers can never be 2 more than a multiple of 4. Let me show you why. Let's take c. C is either going to be a multiple of 4, 1 more than a multiple of 4, 2 more than a multiple of 4, or 3 more than a multiple of 4. Once it's 4 more than a multiple of 4, it's back to being a multiple of 4 again. So it's either one of these 4 cases. When I do 4n squared, I'm going to get 16n, which is 0 more than a multiple of 4. When I do 4n plus 1 squared, I get 16n squared plus 8n plus 1, which is 1 more than a multiple of 4. So the remainder here will be 0, and the remainder here would be 1. When I do 4n plus 2 squared, I get 16n squared, 8 double that 16, n plus 4. What would I get as a remainder when dividing by 4 here? I would get a remainder of 0. And when I square this one here, 4n plus 3 squared, I'm going to get 16n squared plus, that would be 3 times 4 is 12, double it, 24, plus 9. So when I divide this by 4, that will give me 0, that will give me 0, this will give me 1 remainder. So in every single case that C could be, the only remainder that I would ever get when I divide by 4 is 0 or 1. It's never 2. But C, so what I've just shown here, but C squared cannot be a multiple, so it cannot be 2 more than a multiple of 4. So therefore, C cannot be an integer. And it will be that is statement X that is the contradiction. C cannot be an integer because there is no C, there's no integer that will give you a squared value, that when you square it, will give you 2 more than a multiple of 4. So the contradiction here is that C is an integer. I've got C as an integer in my assumption, and C cannot be an integer. That's where the contradiction is. So boom, there's your contradiction. So then you'd write yourself proof. So you'd then write a conclusion which says, therefore, there is a contradiction. So therefore, one of the numbers A or B must be an even number. So So there we are, pretty tricky little proof that one. I don't think it will come up in an A-level question, but I just thought it's an extension question, why not show it you? Let's move on to the second one. Okay, so moving on to the second one then. So for real numbers where x is in between 0 to pi by 2, it's true that sin x plus cos x is greater than or equal to 1. Okay, so we'll start by assuming that the reverse of this is correct. Now, to start with, we know that sin x and cos x are positive when it's in between 0 to pi by 2. Okay, so if it's positive, then we know this is factually correct. So when you add two things that are positive, it's never going to go below 0. So in our assumption, the only thing that I'm going to say is that it could be sin x plus cos x could be in between 0 to 1. Okay, so it can't be less than 1, it can't be less than 0 because sin x and cos x are positive, but maybe when you add sin x to cos x, it could give you an answer in between 0 to 1. It's definitely not going to be less than 0 because they're both positive, and we're assuming the opposite, so it's not going to be greater than or equal to 1. Now what I'm going to do next, I'm going to be a bit cheeky here, is I'm going to square everything. When you've got an inequality that just involves positives and zeros, you are allowed to square everything. So 0 is less than or equal to sin x plus cos x all squared is less than 1 squared. 0 squared is 0, 1 squared is 1. Okay, so let's now expand these brackets. It'll be sin squared x plus 2 sin x cos x plus cos squared is less than 1. Now we know that sin squared plus cos squared will equal 1, so I'll therefore write this as 1 plus 2 sin x cos x is less than 1. Now I'll take away 1 from all three sides, and I've got minus 1 is less than or equal to 2 sin x cos x is less than 0. So therefore, what I've just shown here, what I've now currently got in my inequality, is that sin times cos is equal to a negative value, which is a contradiction. What does it contradict with? It contradicts with sin x and cos x are both positive, because if they're both positive, you can't get a negative when you multiply two positives together. So there we have it. So it's a cheeky bit of squaring inside an inequality that leads us to this contradiction. So there we are. The contradiction is where sin and cos are positive, and here we've got sin and cos, and one of them might be negative. So there we are, that's the answer to this question. The next question is actually very similar, so maybe give the next question a go now that you've seen how to do this one. Alright then, hopefully you have given this one a good go then. Let's have a go at it. So let's just start by having a look at what boundary we're dealing with x in between pi by 2 to pi. Now we're going to assume here that sin x in this region is positive or greater than 0, and cos x in this region, if you remember on the graph, is less than or equal to 0. Okay, so that's what we can assume. We know that that is factually true, and now we'll assume the opposite of this statement as well. So we'll assume, now if I'm taking away something negative, potentially negative, then the answer to this total thing is never going to be a negative number. So I know that assume, so as cos x is negative or 0, minus cos x is positive, and then when you add it onto sine, it will be positive as well. So I know that the sine minus cos is positive. So I'm not going to do anything to do with maybe sine minus cos is negative here. So now I need to assume the opposite of this statement here, which is that it's in between 0 to 1. So it could be 0, sine x minus cos x is less than 1. It's definitely not negative. I know that because of a positive take away a negative will always give you a positive. So I know it's in between 0 to 1. Again, let's square both sides here, or all three sides rather. So it'd be 0 is in between sine minus cos all squared. Let's expand the brackets on that straight away. Sine squared x minus 2 sine x cos x. And plus cos squared is less than 1. Let's now, so 1 squared is 1, that's why the 1 doesn't change. 0 squared is 0, that's why the 0 doesn't change. And let's now, sine squared plus cos squared is 1, so I'll now write it as 1 minus 2 sine x cos x is less than 1. Take away 1 from both sides, so it'd be minus 1 is less than or equal to minus 2 sine x cos x. And that's in between 0. Something I'd like to do as well is I would like to times both sides by minus 1. Now when you times by minus 1, you actually flip over all of the inequalities. So it'd be 2 sine x cos x, which is positive. So therefore, 2 sine x cos x is positive. And not 0, which is a contradiction. Why is it a contradiction? Well, because I've got one positive thing and one negative thing, and it's multiplying together to give me a positive thing, and that's definitely not correct, because if I've got one negative, one positive, I should get a negative thing. So that's where you have it. That's where you have your contradictions. You have your contradictions because you know that sine is positive, cos is negative, and when you times the two things together, you should get a negative. But in this inequality that I've just shown here, I get something that's positive. So therefore, we get a contradiction. So there we are. So that's where our contradiction comes in. And let's move on to the final one. Okay, and let's move on to the final question. Prove that the tangent and radius of a circle meet at a right angle. So let's just remind you of that circle theorem from year 11. We've got a circle, we've got a tangent, and so it should touch it just at one single point. So just remind ourselves of the definition of a tangent. The definition of a tangent is a line, in this case that touches a circle, a line that touches a circle at just one point. That is factually true. Okay, so just remind ourselves of that. And the radius will meet at a right angle. Okay, so we'll meet at a right angle. So what we'll do then in our assumption that it does not meet at a right angle. Let's assume that it's some different angle that it meets at. Okay. So we've got the centre of the circle, the tangent meeting the radius point. This is the radius, this is the tangent. And let's say that this angle here is not a right angle. So let's just say that it's some point further up the line where there is the right angle. So at a different point, at a different point, the radius will meet the line at a right angle. And this point, this hypothetical point where the tangent and the radius do form a right angle, this distance will be shorter than the radius line, than the value of the radius. Now, why is that? Well, because if you've got any line where you have a right angle, if you're any triangle where you have a right angle, then it's never the hypotenuse that's shorter than one of the sides on the right angle triangle. So this is by Pythagoras' theorem. Because now the radius, where radius is the hypotenuse, because the radius is opposite the right angle now. Radius is the hypotenuse. And if the radius is meeting the tangent on a different line, whereby the distance from the centre of the circle to the tangent is smaller than the radius, then the tangent will be meeting the circle at two different points. So therefore, the tangent will meet the radius, also the tangent will meet the circle circumference at two different points. Which is your contradiction, because the definition of a tangent is a line that touches a circle at just one point, and here we've just concluded that the tangent will meet the circle at two different points. So there we are, there is your contradiction. It is a contradiction about the fact that tangents should only meet the circle at one point, and if that angle was not a right angle, then it'd be another line that would create a right angle, and that line therefore must be inside the circle, and therefore if the point of intersection would be inside a circle, then the tangent will go into the circle and will therefore intersect the circle's circumference at two different points. So there we are, there is your contradiction, and there we have, we've finished the whole of this video. It takes a little while to go through these proofs by contradiction, but hopefully you've found the video helpful, you found the examples helpful, and you've got better at proof by contradiction, and maybe in a few months' time you may have to come back to it, but that's absolutely fine. The video is always here for you to help you out. So lovely, yeah, hopefully it's helped, and thanks very much for watching.